get started. First of all, are there any questions about backtracking or the, especially the homework 4 bandwidth problem? Any questions? Has anybody got a working bandwidth program yet? How fast did you, I see one nodding face. How far does your program get?
I've only tested it with like up to 15 vertices right now.
And the reason you only tested it is what? Because it then hit a wall, or because you just got tired of running?
I was able to finish like the 15 vertice, one of the 15 vertice problems in like 5 seconds, I think it was, or give or take a bit. But then like, I know I had downloaded the 20 vertice file and that exploded, so.
Okay, so what happened is you're saying your program made it through 15. And again, this may or may not be true, but I will presumably trust you for now, since the stakes are low. That you were able to get to 15 and you hit a wall when you got to 20. Okay, this may happen. Some of you may hit earlier walls. 15 is not, there are people who will hit earlier walls. Again, if you go and construct all permutations of n items, which is kind of the default thing to do, start out by hitting all permutations of n items. You are not going to get up to 15 factorial. You might get up to 10 factorial. You might get up, something, that's probably about where you would run out of gas. But anybody else get working programs so far? Okay, how many lines long is your program? Ballpark figure.
About 192.
192, okay, and that may be, first of all, as the first one to get it done, that is good. I will say that there probably is a working version that can be gotten under 100 lines, okay? My recommendation is, if you are confused, start by getting backtracking to work to generate all permutations. Then get it to count the, measure the length for any permutation, the length of the longest edge, and find the smallest of those, okay? And then once you've got that going, then I encourage you to start pruning, okay? Any questions about that?
Professor, I have a question.
Yes.
In your directions PDF, you give an example where there's the one vertice with 4 edges, and yes. It says that there's like a distance where like 1 to the last is 4, but each edge is just unweighted, where it's just like 1,
okay,
right?
So what does the backtrack thing mean? What does the bandwidth problem mean? And I think I gave you a graph where, suppose we have a star, I want to say on 5 vertices. Is it 4 vertices or 5 vertices?
5 vertices.
Okay. There are 5, this is an unweighted graph. Okay. If we put the vertices down in the order 2, 3, 1, 4, 5, and we assume that these numbers are spaced 1 unit apart from each other. The length of this is 2, because the edge 1, 2 in this permutation, or 1, 5, are of length 2. Okay. Now there are other permutations. Suppose I put the permutation as being 1, 2, 3, 5, 4. Okay, what would this graph look like? Now the edge from 1 to 4 has a distance of 1, 2, 3, 4. Does everybody see the weights are not a function of the graph? The weights, if in some sense, are a function of the layout. You're trying to put the vertices on a line, okay, and you want it so none of the edges span too long a thing. Okay? Any questions about that?
Thank you.
Okay? Actually, if you want a reason, you may say, why does anyone care about bandwidth? Okay, what is this thing? Well, one area where it comes up is in linear algebra. Okay, you know a graph can be represented by an adjacency matrix. What is an interesting layout of an adjacency matrix? We can kind of agree we can permute the vertices. In an adjacency matrix, we could relabel the order of the vertices. You initially label them 1 to n. If there was a reason why it would help to name them something different, we could do that. There's no reason why we couldn't renumber the vertices in a different number. It'd be the exact same graph topologically. What the bandwidth is really asking us is, can we permute the vertices of the adjacency matrix so all the ones in the adjacency matrix lie close to the main diagonal? That's kind of really what this thing is doing if you think about it, right? If you think about it, you know, if we had it like this order here, from 1 going to n, that's going to be putting a 1 out here. That's bad. If we could permute the number so everybody was close to the main diagonal, that's what the bandwidth problem is saying. Okay? And so your job is to find the best ordering for a given graph. Okay, and if you have one of these matrices, you can do certain computations much easier. Okay, that's why people care about it. Any questions? Any questions about what the problem is asking? Because if you don't know it's asking, you can't possibly do it. Anything, and any other questions or comments?
I'm just curious, can all the example file like be run in 1 minute?
Can all the problems be run in 1 minute? Let's say that's a hard question to answer. Okay, so I am not sure whether or not I have run all of them to 100. Okay, even if I have not, somebody else might do it, right? It's possible people have some super duper computer, or they're smarter than me, or something like this. So it's a little hard to tell. Do I expect anyone in this class to get all the way to 100? The answer is no. Okay, is it possible? I suspect it is possible. Okay,
Good, thank you.
but it would require more and better pruning than I expect you to get. Okay.
Okay, thanks.
In fact, sometimes students will come into class and say, "Hey, I got to 100. And it just took a couple seconds," and then I'll say, "Well, you did it wrong." So, what do you mean I did it wrong? I get an answer. I said, "Well, you're not getting the minimum answer on all of them. You're doing some kind of a heuristic where they'll say, oh, if there's an edge, maybe I should put these things close to each other." But they're not going through enough to guarantee that they always get the best possible solution. And if they don't go through all the answers to get the best possible solution, I am quite sure that on one of these examples, they will fail. Okay? Any questions? Okay, any questions about bandwidth? Okay, I think you have what? You have another week or so on this assignment. Is that correct? When is it due? Okay, here I see people wave on the 3rd. That's
Tuesday.
election day, right? Okay, so hopefully we will have the bandwidth to get through the election day. Okay.
I have a question about
Yes.
question about bandwidth problem.
What about it?
I want to know if we can check whether the given permutation is the solution or not.
Check if the given permutation is what?
Is the minimum bandwidth or not? Can you check it?
Can you check it? Okay, so recognizing that checking if a given permutation is the minimum bandwidth is not easy. checking if the bandwidth of a particular permutation is 3 is easy. What's hard when you say minimum bandwidth, that means that you're proving that there is nothing that is of size less than 3, right?
Yeah.
And that is not hard. That is not obvious to do. Okay. So it's not only a question of showing me a good bandwidth, it's proving to me that you can't do better. Actually, for most of the time in most of the programs is going to be spent proving that you can't do better instead of actually finding the thing. It's not that your program's going to run for 59 seconds and suddenly pop, it finds the minimum one. What's going to happen is it's going to find a bandwidth of size 3 or 4 in a few seconds, and then it's going to grind through all the possibilities to make sure you can't do any better. Okay? That's what I kind of expect that most programs will do. Although there's other ways of writing it so that doesn't happen, but recognize that the hard part is proving that you actually have the minimum. Okay? It might be easy to actually find one that's of that size. Not easy, but it depends upon the graph. Any other questions? Okay, so keep beating on it, and I look forward to seeing the results. Okay, today's problem of the day is a problem on backtracking also. We are asked to generate, it says that a multi-set is allowed to have repeated elements. Okay, a multi-set is a set of items, but there's repetitions allowed. And a permutation of a multi-set, okay, because there are duplicates, there may be fewer arrangements of that element, those elements, than n factorial. Does everybody see that in this case, if we have the elements 1, 1, 2, 2, these are the 6 permutations. There's only 6 permutations, not 24 different arrangements of the multi-set. Okay? And so what I want you to do is to give me a, show me how to construct all the permutations of a multi-set. What multi-set would have the most permutations? Someone give me a multi-set. What multi-set of items on 4 items will have the most permutations?
4 distinct numbers.
1, 2, 3, 4, right? I will have 24 or 4 factorial or 24. And how many, what multi-set of items will have the fewest ones? Okay. When all the items are the same, what if it's 1, 1, 1, 1, 1? Then bingo, there's only one arrangement of it. So we know what we want to create. How do we go about coming up with a backtracking solution for this? What is our strategy here? Somebody. Okay, what does it mean to come up with a backtracking solution? Okay, I'm not hearing anything, not seeing anything. What does it mean? Okay, constructing candidates, that's okay. The first thing I guess you say is you want a vector. What is the solution vector going to be? Does anyone have an idea how I'm going to represent my solution? What is it going to be? I am going to guess that it's going to be, the easiest thing would be to create an array with n holes and n slots, and each one is going to have one of the distinct elements in it. Everybody kind of see it? In this case, for this one, actually in this case, I would have, right, 4 slots, and every slot could in principle be a 1 or a 2. That's kind of what I'm going to be holding in here, right? Okay, so what do I need to do? I need to fill in 3 different routines. One of them is construct candidates. One of them is is a solution, and the other is process solution. Can anybody tell me how to divide the work up among these things? What do I want to do? Someone want to make a proposal? Okay, anybody? What about construct candidates? This is usually the choices. What is the candidate for the ith position?
The number of unique elements.
Say that again, I didn't hear that.
The number of unique elements.
Still didn't hear that. Try it again.
The number of unique elements.
Okay, for some reason, I'm sorry, I'm not getting that. Somebody else, or say it again. Unique elements, okay? So is it, you might be saying that the construct candidates in this case would be equal to candidate 0 is a 1, candidate 0, 1 is a 2, okay? Is this what I do? Is it always, are the candidates for the ith position always going to be equal to 1 or 2 here? Okay. I'm seeing not really. I'm seeing keep counts of 1 or 2. The important thing is, what are my candidates for the third position on this example? It should be clear that if I have a 1 and a 1 here in the first 2 slots, I've only got one choice for the third position. Isn't that right? Okay. So what is the idea here? Basically, what you're proposing is that my construct candidate should not be always 1 or 2. What I should do is basically set up the counts vector. Okay. And what I'm going to start out with is something like, I'm going to say maybe C sub k is going to be equal to the number of element k's in, allowed. So originally, this is going to be represented by saying C1 is equal to 2 and C2 is equal to 1, 2. I'm allowed 2 2s and 2 1s. I could now, for my particular permutation, for I equals 1 to k, if I'm looking for the kth element here, if I've already put down k elements in my permutation, I'm going to say C sub, I want to say A sub I minus minus. Okay. What is this saying? If I read my C properly, I'm going to go through my vector here. And if I see a 1 here, I'm going to decrement the remaining number of 1s, okay, by 1. If I see a 2 here, I'm going to decrement the remaining number of 2s by 1s, right? So C is going to be an array that's going to tell me how many times, how many, members of my original set of that for each possibility are there. Okay. Does everybody kind of get that idea? Any questions? Like a question, I don't get it, it's fine. But now, can we use a hash table for that? You want to store what is the number of elements remaining for each letter, each of your, basically universal set. Okay. And I guess you could use a hash table, but I don't see why, if these are integers, the index of having it be the array seems to me to be a better, the way I would hold it. Okay, I don't see any advantage to a hash table here. But the important point is now you're going to have, after you know the counts, you're going to have a loop for I equals 1 to the alphabet size. Okay, however many letters in the alphabet there are. And what I'm going to say is if C of I is greater than 0, then I is a candidate. Does everybody kind of see what I'm doing here? I know it's looking a little bit cramped now. But what is my thing going to do? My construct candidates is going to count how many free, how many of each letter of the alphabet, each one of my universal sets has not been completely used in the prefix. Okay? Once I know that, I'm going to add any one that doesn't have that count, okay, as a candidate for the next position. Any questions? I don't see enough cameras on to know whether people are getting this or not. Do people see what I was doing here? Any questions or comments?
So
What
sorry.
Yes, what?
Okay, so just so I'm understanding this problem correctly, right? This is basically the same as like the distinct number of ways to arrange like the letters in like Mississippi, for example, right?
Exactly. MISSISSIPPI, right?
Yes,
There's a lot
okay.
of I's repeated and a lot of S's. Okay, if I took the word Mississippi, okay, scrambled the letters, I am not going to get, I don't know how many letters are in Mississippi, but if it's, but it's not going to be that many factorial because there's repetitions. This is what you're trying to do, right?
Yes. So if we do that, can't we sort of do it in a way that we solve like a problem of like determining the distinct number of arrangements in 301, where you like first, like for every distinct set, say there's, I don't know, some variable number of like different sets of items. Like here, there's 2 2s and 2 1s.
Right.
Couldn't we start by placing all of the 1s first and then place all of the 2s and so on and so forth until we just get to the unique number of items? And then once we have the unique number of items.
You're trying to say, if I didn't know better, you're trying to say, if I want to find all arrangements of 1 2 1 1 2 2, you're saying I'm going to go start at the beginning. And I'm going to do what? I'm going to figure out where do I put my 1s? Okay, say again what you're trying to do. Is it because, are you using the fact that there's only 2 different kinds of letters, or are you using everything?
Well, this could be applied, to variable number of things, but we would start by, for each set of numbers, we would place all of those numbers first. So we would place all of the 1s first.
Yeah.
And we would have, whatever, how many different possible places to place all of the 1s. And then from there, we place all of the next set and so on.
Okay, so you're trying to say that you're going to build something where you're going to first put down all the ways of putting the 1s down. Which I think is going to be something like 1. I guess I can put it down also as a 1 1. This is what you seem to be telling me. And then for each of these, you're going to branch with all possible ways to fill in the next letter, right? Now,
Yes.
Notice a couple of things. So this is actually an exhaustive construction of this. Notice you're kind of doing what I'm going to say, a breadth first construction, where I'm doing a depth first construction. Okay, is one difference between what we're doing here. Does everybody kind of see what he's doing? He's saying, I'm going to look at all the ways I can put my 1s down. And then for each of these, I'm going to look at all the ways I can put the 2s down. And for each of these, I'll put all of the 3s down. He is filling this out in a breadth first way. I am actually probably ultimately constructing exactly the same tree that this he is, but I'm going kabunk, kabunk, kabunk. Actually, sorry, that's bad. Bunk, 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 bunk. Does everybody see that I'm doing it in a depth first manner? Where he's kind of thinking about a breadth first manner. Now, what don't I like about the breadth first manner? A lot of things I don't like about it, okay? One of which is you're going to be using a lot more memory than I am. Notice you are constructing all solutions partially before you finally finish it off at the end, right? I am only going to use memory proportional to the size of my solution, which is n. You are potentially doing n factorial of them, right? What would you be doing if they were all unique? You would have said, my first child has a degree of n, and my next child has a degree of n minus 1, and then this thing is going to have a degree of n minus 2. You're going to build all n factorial of them before you print everything out. You got to store that, right? Me, with backtracking, I don't have that problem. So that's one reason why I like what I'm doing better than you. Okay? Any questions about that? Okay, but let's go through this because I think I'm not completely pleased with the degree. Okay, so by constructing candidates, fill in numbers that aren't used yet. Is a solution is going to be basically is k equal to n. Have I filled up my little array, and process my solution will just be to print it. But let's go through how my solution is going to work. This was your solution. Let's go ahead and do it my way. Oh, sorry. I'm hoping this will clear out a little bit. Boom. What is my, uh-oh, trouble. Okay, how would I do mine? This is okay, how do I erase this? Sorry, I'm not doing a great job here. Okay, how would mine work? I am going to set up an array of size 4 for my solution. What are the candidates for my first position here? What are the candidates for the first slot here? I want you guys to yell them out now. Okay, what are my choices? 1 or a 2. I put a 1 in here, right? What do I do now? What are my candidates for the next spot? 1 or a 2. I want people screaming. What are my candidates for the next spot?
2.
2. I don't have 1 as a candidate anymore because I've used them. I have 2 2s left and 1 1. I can put in a 2. And then I put in a 2 and I'm done. I printed out 1 1 1 2. 1 1 2 2. What's my next choice? Do I have another choice for the 4th spot? No. Do I have another choice for the 3rd spot? No. Do I have another choice for the 2nd spot?
Yes.
A 2.
2. Now, once I do that, what are my candidates for the next spot? The 3rd spot?
1 or 2.
1 or a 2. I put in a 1. What are my candidates for the 3rd spot now? I've used all the 1s. I can only put in a 2. I'm done. 1, 2, 1, 2. Do I have any choice here for the 4th spot anymore? No. Do I have any choice for the 3rd spot? No. Do I have any choice for the 2nd spot? I am going to claim. What? Actually, I did. This 2 was still available here. Excuse me. My slot. I got a little sloppy. There was no choice for this one, but I still had. This could have been a 1 or a 2. I still have a choice of making this a 2. If I make this a 2, what is my other choice for the last one? 1. I get 1, 2, 2, 1. Now, do I have any other choice for my last one? No. Any other choice for my next to last one? No. Any other choice for the, I put down a 2 here. Any other choice for this? No. Any other choice for the first position? The answer is yes. I haven't tried a 2 there. Now I put down a 2. Maybe I'll do it in a different color just to make me a little bit more exciting. Now my choices for the second position are what? I'm going to argue a 1 or a 2. If I put a 1 in there, what is my next thing? What choices do I now have for the third position? What are my choices for the third position? Somebody.
1 or 2.
1 or a 2. I put in a 1. What are my choices for the third position? For the fourth position?
2.
Only a 2. And bingo, I got another one. 2, 1, 1, 2. Do I have any other choice for the fourth position? No. Do I have any choice for the third position? Yes, I can replace it with a 2. If so, what are my choices for the last position? Only a 1. And now 2, 1, 2, 1 is acceptable. Now, do I have any choice for this position? No. This position, I've blown it. This one, yes, I can put a 2 here. What choice do I have for the third position if I at this point? Only a 1. And the last one is only a 1. Any questions about how I implemented this? Okay. This is important to kind of be able to do this kind of thing, to be able to see how these generation problems work with backtracking. Okay.
Professor,
Yes.
I had a quick question about this question. I see that this is a clever algorithm, but I don't necessarily see how this is backtracking, because to me, it looks like every solution that we come up with using this method will be unique, and we won't have to backtrack to verify it, because we can pretty much variably prove that everything.
Okay, so how do I, why do I know this is backtracking? I'm implementing these 3 subroutines, and I'm calling them within a program stub that's called backtrack. So yes, by definition, this is backtracking. Okay, this is what it is, and not much more to it.
Okay, so this is just like the most by technicality, this is backtracking.
No, okay, not by just by name, by definition.
We're saying that.
Where is the backtracking? The backtracking is happening when I run out of candidates at a position. I bomb out of a recursion, an instance of the recursion, and go back to the previous position. The forwarding or backtracking has to do with which slot in the solution vector am I working in. If I had to take a guess, if you had to plot the motion of this thing, it's probably looking something like ka-chunk, ka-chunk, oh, sorry, I hate when it does that. Ka-chunk, ka-chunk, ka-chunk. Maybe back here, ka-chunk, back here, ka-chunk, ka-chunk, back here, ka-chunk, 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 ka-chunk back here, bump, 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 something like that. The backtracking is the moving back and forth among the positions. Okay, that's where the backtracking is.
Okay, so I was getting that confused with pruning, which we're not doing.
Pruning, you're not doing any pruning here. Actually, well, yes, you are. Okay, let's just think, what is pruning? Pruning, if you need to know what pruning is, it's identifying exactly what are the minimal set of elements at each slot. What might have been an alternate way to have done this job? What if instead I said for construct candidates, always give me 2 candidates. Is a solution when it's full, and then process solution. Check if the counts in A equal the counts in the set. If so, print. Does everybody see that I could have alternately done this in a kind of a clumsier way? Always allow both letters of the alphabet in any position. And then once you filled the array, check to see whether or not the distribution, this is the first time I've seen this. Is this the first solution time I've seen that solution? Okay. And this does not do any pruning. This is going to construct n factorial things regardless of what the letters are. The cleverness is that we restricted the candidates to making sure that we never used more of a count than we needed to. That is what the pruning is. It's making sure that you're exploring the minimum number of things that you need to do at every step.
Okay, so pruning doesn't necessarily only apply to the tree itself, but also to how we construct the tree in the
Pruning
first place.
is what are the possible, right, what are the candidates that you're considering at each node in the tree? Okay, some paths may die before they hit the full length, and maybe that's what you think of as pruning. But anything I can do to keep my tree smaller is what I think of as pruning. Okay? Any questions? Okay, fair enough. Okay, again, it's important that you write your first and experiment with your first permutation generator. Then all of this will be a lot more concrete. Okay? And while it, you know, it requires, it's not a complicated algorithm, but it requires a little bit of intricacy and debugging, I suspect, the first time you have to do it. So go ahead and make that happen. Any other questions about backtracking? Okay, I would like to now shift gears and talk about another algorithm design paradigm. We've seen about graph algorithms. We've maybe seen about brute force search, which would be backtracking. We've seen all kinds of different things. Dynamic programming is an optimization technique that is very, very useful for things that have an inherent left to right order on the items. Now, what things have left to right order on the items? Character strings, schema, the letters appear in a particular left-right order. So character strings have a left-right order. Trees, if you have a kind of a label, binary search type tree, the leaves tend to have to appear in a particular left-right order. So sometimes things on trees are like that. But once you understand dynamic programming, it's a relatively simple idea. But until you understand it, people tend to think something weird's going on. What I would encourage you to do is look back at the daily problem. We talked about Floyd's algorithm a little bit. That was an example of a dynamic programming algorithm. The daily problem I did on the shortest path using exactly k edges was a really good example. And so I'm going to go through dynamic programming from the scratch, but people sort of understood that when I talked about it. And if you're feeling confused, that's worth looking at again. But we'll try to work from scratch now. Any questions? Okay. So what do we like about backtracking? Backtracking is an exhaustive search algorithm. Backtracking is going through all possibilities. Why do I know your bandwidth programs should be correct if you do them in a, unless you make a bug? Well, you're searching through every possible permutation. implicitly. You're picking the best one. Are you going to find the optimal bandwidth solution? If you try all solutions and keep the best one? Yes. So correctness from exhaustive search should follow pretty easily. Now, some other optimization problems, like minimum spanning tree, we made a local choice at every point. Grab the next edge, grab the next edge. And only for certain problems are we guaranteed to get the optimal solution to the final full problem by being greedy at every step. That's why it's kind of amazing minimum spanning tree worked. Dynamic programming philosophically is a way of giving an algorithm that is going to search through all possibilities systematically, which is why I'm going to know it's correct. But it's going to store results to avoid recomputing, which is why it's going to be fast. Okay? And there are a bunch of problems where this kind of can be done. And I'd like to try to illustrate, the basic principle today on a couple of simple problems. And it's important to make sure you understand how the mechanics of this thing is working. Okay, so what do I want to say? I want to start out by saying, let's remember what a recurrence relation is. You took AMS 301, you did a lot of recurrence relations. If not, you should know that a recurrence relation is an equation defined in terms of itself. So this is a recurrence relation. A of n equals A of n minus 1 plus 1. It's an equation where the right side depends upon a smaller value of the same series. Okay? And if you're given a recurrence relation, a recursive formula, and a initialization condition, this can generate some other kind of formula. So this, in fact, if you look at it, for A of 1, it's going to give us 1. For A of 2, it's going to give us 1 plus 1, or 2. For A of 3, it's going to give us 2 plus 1, or 3. Does everybody see that this recurrence relation generates the function A of n equals n? Okay? In fact, any polynomial, there is a recurrence relation that generates it. Here is another recurrence relation. A sub n is going to be equal to 2a of n minus 1. If we start out with a of 1 equals 2, the first element is 2. A of 2 is going to be 2 times a of 1. A of 1 is 2, so it's 2 times 2, or 4. A3 is going to be 2 of A2, or 2 of 4 times 4. A of A2, or which is 4, 8. Does everybody see that this recurrence relation generates the exponential function 2 to the n? And if you don't see it, I want to say a question like, I don't see it, is a good question. Any questions? Okay. So we can generate all polynomials, all exponentials. We can also generate a variety of weird functions very naturally with recurrence relations. What does this weird function have to do with? Okay, this is a of n is equal to n times a of n minus 1, where a of 1 is 1. A of 1 is 1. A of 2 is going to be 2 times a of 1, which is 1, so that's going to be 2. A of 3 is going to be 3 times a of 3 minus 1, or 2. A of 3 is going to be 3 times the previous value, which is 3 times 2, or 6. A of 4 is going to be 4 times a of 3, or it's 24. Does everybody see what weird function am I generating by this recurrence relation? Does anybody see what weird function is being generated? Anybody?
Factorial.
N factorial. And you may say, wait a second, n factorial isn't such a weird function. I know what it is. If you think about it, the only reason you know about it is people gave it a weird notation, this exclamation point. What is 2.5 factorial? Can anybody tell me what 2.5 factorial is? You can't. It's only defined on integers. It's not like, it's a kind of strange function. Okay? But again, a lot of functions can be generated by recurrence relations. And if you give me a recurrence relation, I can easily evaluate what the recurrence relation is by basically writing a recursive program to do so. Any questions about that? Okay. Okay. The most famous series, perhaps, that is generated using the recurrence relations is the Fibonacci numbers, okay? Where we say the nth Fibonacci number is the sum of the n minus first and n minus second Fibonacci number. So here, because this is a recurrence with a history of 2, we need 2 initializations. We say the 0th Fibonacci number is 0. The first Fibonacci number is 1. What is the second Fibonacci number? By this, somebody. It's going to be
1.
1. It's fib of 1 plus fib of 0, which is going to be 1. What is the third Fibonacci? This is the first, 0th, first, second. What is the third Fibonacci number?
2.
2. Okay. What is the fourth Fibonacci number? Should be 3, 5, 8, 13, 21, 34, 55, ... Okay. Has everybody seen the Fibonacci numbers? I'm kind of assuming you've seen the Fibonacci numbers. How many of you have programmed the Fibonacci numbers before recursively? This is usually the first recursive program anybody writes. This is it, kind of the Fibonacci number, right? If n is equal to 1, 0, return 0. If n is equal to 1, return 1. Otherwise, return the n minus first and the sum of the n minus first and the n minus second Fibonacci number. Does everybody see, and if not, this is important to understand, that this recursive program computes the Fibonacci numbers? Is there any question about that? Like say that again or anything like that? People understand this recursive program? Any comments about it?
I do have one question. Why do
Yes.
we return a long?
Why are we returning a long? The reason is long is a long integer, okay? And Fibonacci numbers get pretty big, okay? So it's very, it's probably by the time you get to fib of 60 or something like that, okay? The size is going to be too big to fit in a 32-bit integer or maybe even a 64-bit integer. And so that's why I wanted the longest integer that my programming language lets me have. That's why I said long instead of int. Okay? Any other questions? My question is, what is the running time of this algorithm? This is one I want you to think about and is the heart of the mystery of dynamic programming. This is an innocent looking program. What is the running time of this algorithm? Does anybody see anything? Okay. It's going to be equal to the number of recursive calls. I'm hearing somebody say it's 2 to the n. Why do they think it's 2 to the n? Does anyone want to confess why they think it's 2 to the n? Okay. It's not, But actually, since you say it's O of 2 of the n to O, big O of 2 to the n is actually correct on some level. Okay, why is that? Does anyone want to say, why did he say 2 to the n? Anyone want to make an argument of that? Well, okay, it's a tree-like thing, okay? And I guess the way to think about it is, this is the cost of the cost of this is going to be the size of my recursion tree, right? And you're saying that the compute fib of n, it's going to be making 2 recursive calls. So you are thinking about a binary tree where to compute fib of n, I am going to have to solve 2 smaller problems. And each one of these is going to solve 2 smaller problems. Okay? And at each point, the argument goes down either by 1 or sometimes more than 1. Sometimes it goes down by 2. On one side, it goes down by 2. On the other side, it goes down by 1. Okay? So you could be saying this is going to be a tree where at every node, it's going to branch by a factor of 2. And the height is going to be at most n. Because the longest path is going, the argument is going 6, 5, 4, 3, 2, 1. So that's a reason to think that it is actually 2 to the n. In fact, it's a little bit less because if you look at it, it's not a complete binary search tree. It's not a complete binary tree. In fact, on this side, the height is only half of what we had before. Okay? But if you want to know exactly how long this is going to take, it turns out that f of n, the nth Fibonacci number, is roughly equal to 1.61803 to the n. This number here is called the golden ratio. Okay? If we look at this tree, the Fibonacci tree at the lowest level is going to is going to the leaves. Fib of 1 is going to be 1. Fib of 0 is going to be 0. 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 0. Okay. In order to get a number as big as this, we are going to have as many leaves. The leaves are all going to be 0 or 1. Any given node, the value of the Fibonacci number is summing all the leaves below it. In order to get the number as big as this, okay, you're going to have to make basically at least 1.61 to the n different recursive calls. So in fact, the Fibonacci program run recursively is an exponential time computation. This is a humbling thing if you've never done it, okay? One of the most instructive program I wrote when I was a punk kid undergrad computer scientist class was that I did a recursive Fibonacci program in assembly language back in those days, okay? And I was astonished that by the time I got to n equals 45, it wasn't moving, okay? This is because it was exponential, okay? And, and that's going to cause a problem. Any questions? But is there a way to compute Fibonacci numbers that is faster than this? Okay? How might we compute Fibonacci numbers faster than this naive recursive program?
Professor, since if you look at the tree, you're constantly using similar values. So like the f of 0 and the f of 1. If we were to just like store it in an array or something, we could just refer back to those values.
The key idea here that you're seeing is that there is repetition in what I'm doing. Let's look at what the recursion is doing. It's calling this, 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 this. Finally, I know what fib of 2 is. It calls this, it goes back to up to this point in the recursion, and it now calls this. Even though here we know that fib of 2 is going to be equal to 1, it goes back and does it again. When we get to here, we know what fib of 3 is, but when we go over here, if we're just doing a naive recursion, it's going to do this computation, this subtree again, even though it had already evaluated that subtree. It's going to do this entire subtree again, even though it had already evaluated that subtree. So the question is, can we store the answers instead of recomputing? That's what you're actually saying. And that is the critical idea behind making dynamic programming work, okay, work efficiently to evaluate the recurrence relation.
Isn't that known as memoization? Yeah, memoization.
Okay, so is it known as memoization? One way to to take that recursive Fibonacci program and avoid recomputing is to keep a recursive program. Note that this is still recursive, fib sub c, fib sub c, fib sub c. But we're going to have a global array, f, that is going to store what the value of the ith Fibonacci number is, right? When I initialize this, do you see how I'm doing it? F of 0 is 0, f of 1 is 1. Originally, I'm now going to say every other value, f sub 2 through f sub n, these are unknown. I don't know the answer yet, okay? And then, when I ask to compute fib of n, it's going to start going through this recursive operation, okay? If I am asked to compute f of n, I am going to do it, okay, by, if f of n is unknown, then I'm going to have to compute it. And what am I going to do? I'm going to call fib of n minus 1, fib of n minus 2. Once I have that, I'm going to store that in fib of n. And then if I've done that, no other recursive call is ever going to call fib of n again. We're going to kind of store the results here to truncate the recursion, right? Does everybody kind of see what we're dealing with? We are here, still having a recursive algorithm, but we are storing things and looking them up in a table before we recompute it. Does everybody kind of get that idea? What is the recursion tree of memoization going to look like? Any questions about this? This is a good practical technique that's kind of halfway towards dynamic programming. Okay. Okay. You're saying it'll be a linked list. What's a linked list? I'm storing my Fibonacci numbers in an array. I have a global array I allocated. See, this is a global array. Okay. And any questions? Any questions about this memoization idea? Okay. If I did that, what's going to happen if I executed a recursion, my recursion here? Let's go back to this horrible thing. I'll try to erase. What is the flow going to be? I'm going to want to compute fib of I'm going to want to compute fib of 6. I'm going to call this recursive thing. I'm going to call this recursive thing. I'm going to call this recursive thing. I'm going to call this recursive. This is 1. I have it in my table. I'm going to look up this. This is 1. It's in my table. Now I know that fib of 2 is going to be equal to 1. In order for me to compute fib of 3, what am I going to do? I'm going to go to fib of 1, but now fib of 1 is in my table. So I'm going to add 1 more, and fib of 3 is going to be 2. For fib of 4, what am I getting? It's this 3 that I look up in my table, which was 2. And fib f of 2 was equal to 1. This is where I stop. This is a 1. That tells me that fib of 4 is going to be 3. When I now go back to compute fib 5, I call fib 3, but fib 3 I can look up in my table. That's equal to 2. Fib of 5 is 5. 5 of, now I get back up to this thing. I need to know fib of 5 is 5. Fib of 4 is 3. This is 8, and I'm done. Does everybody see that if I store the results and look them up beforehand, the tree that I am using is only going to be something like this. And it's going to be basically linear instead of the whole tree. Any questions about that? Okay. Okay, so memoization is a hack to your program to make your recursive programs faster by storing things explicitly and looking them up before making the call. Okay. In fact, this would give us a linear time Fibonacci program. But it's pretty, you have, this to me isn't obvious. Can anybody have any other idea how to compute? Yeah.
Technically, this doesn't really need to be recursive. If you just have 0 and 1 in an array, and then you just keep adding the last 2 values until you reach the.
You're saying, I don't want. I know that recursion, that Fibonacci numbers are defined by recursion, but I don't want to actually implement it by a recursive call.
Mm-hmm.
I want to do the following, okay? I want to say, what if I set up an array F, again, like I did before, 0, 1. And now, instead of calling things recursively, what if I have a loop that just takes the last 2 elements and stores them up, adds them up? The next one is going to be 2. The next one's going to be 3. The next one's going to be 5. The next one's going to be 8. The next one's going to be 13. The next one's going to be 21, 34, 55, 89. Okay, does everybody kind of see that?
Mm-hmm.
Note that this is a for loop. What happened to the recursion?
It's gone.
It's gone. Where did it go? Okay. I found a clever way to evaluate my recursion, not recursively, but by storing the elements in the table, so I knew that they would be there when I looked them up. And I filled in the cells in my array in an order where the elements were already there, okay, to compute the next value. This is what dynamic programming is, okay? It is taking a recurrence, okay? We're going to add space to store partial values, okay, to save us time. And we're going to, instead of implementing it as a recursive thing, we are going to evaluate the recurrence from, instead of, usually when you make a recursive call, you go from f of n and it calls smaller things. Instead, I'm going to start from the smaller things and build up what I know and store it in a table. So the next value I can compute because I know that the other 2 numbers are still there. That is what a dynamic programming is. Any questions about that?
Yeah. Can't we use an array of size 3?
Okay, so
Because
you're saying, oh, look, he's using an array where he's storing all the Fibonacci numbers. If I really wanted to be clever, I could get away with less storage because I only need the two previous values. Okay? And I will give you that. Okay? But it's clear that if you do that, it's still going to take linear time. It will just take a constant amount of storage instead of n storage. Not that that's necessarily a bad thing, but to keep it simple, this is my Fibonacci program. I set the initial conditions, then I evaluate it from the bottom up, from fib of 2 to fib of n, knowing that the two numbers I need are already in the table, so I can just look them up. What is the running?
So dynamic programming, so like the original one, we did it recursively. The reason that wasn't dynamic is because we used no additional storage at all. But this is because we're using the array. And
No, the other one, by the way, also used storage. Okay, let's think about it. This thing is using this storage explicitly. The memoization solution also used the storage, right?
Oh, I wasn't talking about the memoization one. I was talking about the original one where we were making a series of recursive calls and calculating over and over again.
The recursive one, you did not use any such storage, except that you had to actually store activation records on a stack, right? There was some kind of implicit storage of recursive calls, which could take actually order n storage, because to compute fib of n, you had to eventually go down and store fib of 1, you know, the activation records for it, okay? But there's no explicit storage here. Okay, do people see what I mean by the recursive thing? If I try to compute fib of 5, what am I going to do? To compute fib of 5, I'm going to have to call fib of 4. Compute fib of 4, I'm going to have to compute fib of 3, fib of 2, fib of 1. And then, so there's kind of a stack of activation records that's n deep. If you make
okay, so I'm just getting a little confused on what dynamic programming then refers to.
What is the difference of dynamic programming? Let's look at these three solutions. This solution is recursive, slow, because you didn't evaluate it. Does everybody kind of see that that's what this solution is? Recursive and slow. Sorry, I've got a problem here. What am I doing? Okay, my machine has, okay, uh-oh, trouble. This was recursive slow. Memoization was still recursive, but it was fast because I stored it. Does everybody see that? This is recursive fast because I stored the values instead of recomputing them. Dynamic programming is, if we look at it, it is loopy, it is iterative, fast, right? Does everybody see there is no recursive thing here anymore? That is the hallmark of what I call dynamic programming. And dynamic programming is a way of taking a recursive program, a recurrence relation, evaluating it in an iterative manner by storing the results. And I like it better than memoization because by thinking this through to store it properly in a table, I will know what its running time is in a way someone with doing memoization usually doesn't know. Okay? Any question? I think I've done this in more detail than I would like, but any questions about the Fibonacci recurrence? Okay, let me show you one other example. Again, I can give you my speech why I love it, but I'm not going to, don't have time for the speech now. What I'm now going to show you is a way to use to compute binomial coefficients. You know the thing, what, you know, n choose k? N choose k is the number of ways of picking a subset of k things out of n. How many people have seen the binomial coefficients before? Wave your hands if you have. Okay, now, okay. Anyone, now wave your hands if you haven't. Okay, okay, so binomial coefficients you've seen. How would you compute what n choose k is? 5 choose 3. How do you compute what 5 choose 3 is? Does anybody have an idea? Those of you who have seen binomial coefficients, what is 5 choose 3? I see someone saying it's 5 factorial, 3 factorial, 2 factorial. Okay? Does everybody agree that there is this formula you saw that n choose k is n factorial divided by n minus k factorial divided by k factorial? Is this a good way to compute n choose k? What is 100 choose 99? Does anybody know how to, what that value is? How many ways are there to choose 99 things out of 100? Well, I'm seeing it's 100. It's because basically your anything that is not the one you choose is it, right? So everybody sees that that's 100. Did you do this by starting out and computing 100 factorial? 100 factorial is bad news to compute. Why is that? It's a number with, you know, several hundred digits, with presumably a couple hundred digits. Okay. How can you compute n choose k? I claim in high school you saw Pascal's triangle. Does everybody remember who here saw Pascal's triangle? May not remember why you saw it, but does everybody kind of remember seeing Pascal's triangle? What was it? Kind of, sort of, yeah. What was it? It was this triangle thing where at every point you started, the outside ones were 1, and then every value was the sum of the two elements above it. So that's 3. This is 3. This is going to be 4 because it's 1 plus 3. This is 6 because it's 3 plus 3. Does everybody remember how this worked? You had ones on the outside of the triangle, and you went above it, and it was the sum of the two elements right above it. Now, why did your teacher make you do this? Okay. Part of it was to keep you probably busy and quiet at some point, to build the first 10 rows by practicing your addition. But what they were really doing, why did Pascal care about this? Pascal cared about it as a way to compute binomial coefficients. Okay? What did Pascal do? How many ways are there to form a subset of k things chosen from the numbers 1 through n? I claim that if you have a subset of the elements 1 through n, of k elements from 1 to n, either it's going to include n as the biggest value, or it won't. If you are going to include the big n as the biggest value, how many ways are there left to finish this? Okay. You have the numbers 1 to n minus 1 to finish the rest of the slots, and you now have k minus 1 slots to fill in. So the number of ways of picking k things out of n where n is included is n minus 1 choose k minus 1. the number of ways of doing it where the biggest element is not n means now you've still got k slots to fill. And the biggest possible number is not n anymore, but n minus 1. So this is n minus 1 choose k. Notice the k here and the k minus 1 choose there. Every subset of size k either includes, okay, n, or if it includes n, it's counted here. If it doesn't include it, it's counted here. The sum of these two is basically C of nk. And this is exactly what Pascal was doing with his triangle, right? How many ways are there to come up with a subset? What is, this is, I think, 5 choose 2. That's 10, if I am correct. Is 5 choose 2 10? I don't believe it is. I claim that 5 choose 2 is the same as 4 choose 1 plus 4 choose 2. What is 4 choose 1? 4 choose 1 is going to be 4. 4 choose 2 is going to be 4 factorial over 2 factorial over 2 factorial. 24 divided by 4 equals 6. Does everybody see how Pascal's triangle is computing the, the recurrence relation? This is a recursive equation to compute this binomial coefficient in terms of these two binomial coefficients. Does everybody kind of see that? Okay. If that's true, that if it's a recurrence relation, you need to have a basis case. What were the basis cases for Pascal? Okay. Well, the main basis cases were 1. Okay, that was the ones on the outside. And I claim that the basis cases are, well, one possibility is that we get to a case where we're choosing k out of k. How many ways are there to choose k out of k things?
1.
1. The other question is, n choose 0. How many ways are there to choose 0 out of n things?
1.
1. Okay, so these are the basis cases. This is the important thing I want you to see and understand. This is an implementation of using dynamic programming to evaluate that binomial coefficients, okay, recurrence. What are we going to do? We're going to build a table BC, which Natalie stands for binomial coefficient, where we're going to build a table where the top thing, if it's going to be n choose k, there is an n dimension and a k dimension. And we're going to start out by saying, for all I up to n, I choose 0, okay, is going to be 1. If this is supposed to be, again, it depends on how I'm going to do. I guess, which is it? Let's say this is going to be 0, 1, ... to k, 0, ... 1 to n. I need, this is going to be setting when k is equal to 0. This is going to be setting it to be 1. So the initialization is filling that row of this thing is filling that row of the table up by 1s. The second case was where we have, what is j choose j? That is going to be a diagonal. And these elements of the table are all going to get set to 1. Everybody see that ij, that's going to get set to be 1. Now, how do we fill this in? Well, this over here is going to be, this is going to be, let's try to write this thing out precisely. 0, 1, 2. What do I now want to do? I'm going to go have outer loops I and j, and I'm going to fill these things in actually along the diagonals that I can. The first row is here, the next row is here. This cell, okay, which is basically going to be 2, 1, is going to depend upon 1, 1 and 1, 0. This is going to be the sum of this and that. That's going to be 1. This cell here is going to be the sum of this one and that one. So let me now make these numbers maybe a little clearer. This should be a 2. This spot is going to be this sum plus this. That's going to be a 3 because it's a 1 plus 2. This one is going to be a 1 plus 2. That's a 3. What's the next row that I want to do? I want to now go through the next column. This is going to give me 4, 6, 4. Does everybody kind of see what I'm doing here? Let's keep making this a little bit further. The next one is going to be 5, 10, 10, 5. Okay. Does everybody see that how I am filling in this table? This is an important thing to be able to see. Okay, how do I do it? I am going to be keeping my I is kind of my n value. That's going to be, I think this is what I is going to be. My I loop is going to be going on this dimension. My j loop, which is going faster, is going on this dimension. And basically to compute each cell, it's going to go to compute any given cell. It's going to go to I minus 1, okay, which means to the previous one, j minus 1, and I minus 1j. Does everybody see the mechanics for how this is working? I'm hearing shaking no's, okay? I want you to think about this, okay? Unless there's a question. Is there a question here? Does everybody see how I am building up a table exactly equal to Pascal's triangle? Okay. What is the running time of this algorithm? Okay. I claim that in order to compute n choose k, I've got to fill up n times k cells. Actually, or to run this thing, yeah, basically if I have n and k, okay, I am going to run this thing through. I'm going to fill up the whole thing. This is going to fill in basically actually n times k or n times n cells. Okay. How much time does it take to fill in each cell? Okay, my claim is it's going to look this item up in the matrix. It's going to look this item up in the matrix. That took one step. Adding them together took one step. It copied here. For each one of these cells, okay, it is spending order n. It is spending constant time in each of these n squared cells. So n squared times 1, this is an order n squared algorithm to compute Pascal's triangle. Any questions? Okay.
Is just to clarify for the n squared, is that because you only have to compute each index only once? So eventually you're just going to compute all of them once?
Yes, exactly right. In order for me to compute nk, Actually, the way I've done this, I might have, it looks like the way I'm evaluating full rows. And only when I finish my full row will I then look this thing up. So this, I think, is an n squared implementation. I think I can do it at nk if I did this the right way. But what's the important point? The important point is I am building a table that is, okay, has nk elements, or actually n times n elements. That's really what a triangle is, right? There's n rows, each of which has on an average n over 2 elements. Okay? So this triangle storage is going to be something like n squared over 2 elements. To compute each element, I'm going to add up the 2 elements before it. It's going to take constant time. This is an order n squared algorithm to evaluate Pascal's triangle. Any questions? There's no questions. I want you to think about it. God forbid, read the book. Okay, look at the code on this. Okay, it's important to be able to see why this recurrence works and how I implemented this and why it is n squared. Okay, think about it, and I'll be delighted to answer questions next time. Any questions? Okay, thanks for your attention. I will see you next class. Okay, bye-bye.